Boris Rozovsky, talking about generalized Malliavin calculus.
Jonathan, I'm mostly interested in stochastic PDEs. But last summer, I bumped into Malliavin calculus because we could not proceed with what we were doing with Sergei Latotsky and Boris Rozovsky on elliptic.
Of course. Talk louder. Or turn it on.
Thank you. Better? Very good. So most of us here are working on stochastic PDEs with say of this type, with say W dot space-time white noise. And this area has been researched a lot. Almost everybody in this room wrote at least 5 papers on this subject, and many beyond. But it is not the case with elliptic PDEs, especially elliptic PDEs of say something similar to this, but with spatial white noise. Actually, I should move here. So elliptic I found a mistake immediately. Examples of elliptic PDEs. It should not be, T should not be here. Elliptic PDE should be something like this. Suppose you have an area, and you have in this area, say, and you have say, L u of x plus m u of x times just spatial white noise. You have some conditions on the boundary, of course. Should be equal to something. U on the boundary should be also something, might be deterministic, might be random. L and M are partial differential operators. And in principle, quite a few work was in the case where M is 0. This is elliptic PDE, not 0, sorry, where this part is, say, 1 or some operator Q which depends only on X and is independent of U. Then it is elliptic SPDE with additive noise. And there is quite a few work, and we understand this area pretty well. But mostly we know that beyond d equal to 4, there is no classical solution, reasonable classical solution. A lot of work on this was done by Marta Sanz, for example, and other authors. Now, the situation with bilinear SPDE could not be better than just additive noise. It should be something like this. So, first of all, there is no reasonable filtration in dimension larger than 2. So you could not talk about any eta calculus, any non-anticipating calculus. You have to resort to anticipating situations, and that immediately leads you, say, to Skorokhod integral or Malliavin divergence operator with respect to, say, white noise. There are more complicated examples like this, where noise is not linear but exponential, and there is a lot of work on this done in Europe, Norwegian school, Zhang, Oxendal, and many other people. Now, general elliptic SPDEs were not seriously considered. We could there is a couple of papers on this subject, but it's only a beginning. And I would go on a limb and predict that it would be a large area. It will be a large area. There is a lot of things which go for this area. There are interesting examples. There is developed technique. It's natural. Consider elliptic stochastic PDEs. Now, I would like to finish my short introduction by adding an example which seems to be completely unrelated. It is a parabolic SPDE, very simple, only with one coefficient sigma, and sigma squared is larger than 1. Actually, Krylov in his lecture considers the same equation only with sigma squared less or equal than 1. It's a generalization of, say, equation like this. Say AUXS plus sigma UX W dot S. And general condition for well-posedness is 2a minus sigma squared would be strictly positive. Why this example is related, we will see a little bit later. Now, so we are not simply in Malliavin calculus, but in generalized Malliavin calculus. By generalized Malliavin calculus, we understand Malliavin calculus not on real valued or normed space valued processes, but on generalized processes in the space of generalized functions. It seems very extravagant, but as a matter of fact, very simple examples lead us to this setting. So, and that is the example which we are considering. It's not SPDE. It is ordinary differential equation with Malliavin operator with respect to one Gaussian variable. Now, very easy to show that there is a unique solution of this equation. And this solution is given by Cameron-Martin expansion, formal Cameron-Martin expansion, when U sub n is a projection of U on the Xi sub n, and Xi sub n means the nth element of the Cameron-Martin basis with respect to Xi. Now, we also can find the coefficients easily, and we will find that U0 is 1 and Un is square root of n factorial, which means that the variance is infinity. And so the solution accordingly is a generalized random element. It's not adapted, so it calls for anticipating calculus, and anticipating calculus is Malliavin calculus, but Malliavin calculus is not developed in the case of generalized functions. What is happening here in this example is actually very indicative for the whole problem. It's the same effect as in this example. In this example, that is the boundary of non-degenerate, this is the boundary of degeneracy. As soon as you cross this limit, equation becomes degenerate and blows up. It turns, as you see on this example, for elliptic equations, you don't see it on this example, but in general, on elliptic equations, the threshold for degeneracy is reached much faster than in parabolic. Essentially, if this does not hold, immediately everything blows up. And in some sense, the deterministic part of the equation does not help. Now we need, say, to cope with examples like this, we need to develop also not simply generalized Malliavin calculus, but also should be nonlinear. We should be able to work with, integrate with respect of nonlinear, with respect to randomness, generalized functions. It's more or less known that it is, say, Malliavin divergence operator or Skorokhod integral with respect to, say, exponent of white noise could be is well defined. It was done again in the setting of weak calculus. But as a matter of fact, there are some substantial difficulties for more general nonlinear noises. Now, what would you do? So what's happening in this example? Instead of considering equation, we are considering a Fourier series corresponding to this equation. Like in Navier-Stokes, people often, instead of Navier-Stokes proper, take Fourier transform and considering a system of deterministic equations. and often don't even differentiate between these two objects. However, not always results for Fourier systems are the same as for the original equation. That is exactly what's done here in this example. Instead equation itself, I'm considering the system of stochastic Fourier coefficients. If it was square integrable, this system would give a classical solution. If it's not integrable, it's just system of Fourier coefficients, and you have to sum them up somehow. So what physicists do in this case, they're rescaling. That is a typical example. The Fourier coefficients grow too much. Borrowing from Takis Suganidis, who gave a talk at Brown a month ago, he was talking about homogenization, and he was saying that in homogenization and ergodic theory, the expansion becomes, when you go further and further, becomes smaller and smaller. So you could not see it actually. What do? You take binoculars, you enhance your frequencies. And in this case, again, you have to take binocular, only you have to turn it around, and which will make your coefficients comparatively uniform. So, conclusion, Malliavin calculus for bilinear SPDEs with stationary noise must be balanced by appropriate weighting. Now let us recall the notation from standard Malliavin calculus in the setting which was used by David Nollart in his book. So we have an orthonormal basis U, Gaussian white noise, which is essentially just a linear combination of Gaussian one-dimensional random variables, standard. If U is infinity-dimensional, of course, the variance of Navier-Stokes is infinity. And we will keep the following notation. F will be our probability space. F, calligraphic F, is sigma algebra generated by Gaussian random variables. L2Fx is a Hilbert space of square integrable F measurable X valued random elements. All right. Now we have to introduce Cameron-Martin. It is a bit, where did I put it? So I will need them throughout the, better? Whoa. Can we there is a distance problem. No. Technology does not work. Maybe that one. Probably this one would work. All right, memorize it. And it's easy to memorize. It's just a multi-dimensional combinatorics. Instead of numbers, we have vectors. Vectors are, all elements of vectors are positive. A plus B is sum of coordinates. Length of alpha, sum of coordinates of alpha. Alpha factorial, product of the elements. Alpha, if beta less or equal than alpha, which means that each element of beta is less than corresponding element of alpha, is this difference. And you could take combinations of beta out of alpha again in the standard way. 0 in parentheses will be zero element. Epsilon sub I will be multi-index, which has 1 at coordinate k if k is equal to I and 0 otherwise. And epsilon of 0 is 0. And Cameron-Martin theorem tells us that Xi sub alpha is a orthonormal basis in L2 on omega. And of course, elements from L2 fx could be expanded in stochastic Fourier series. And the norm is computed as sum of square of norm is sum of squares of exponent of Xi alpha with V. That is exactly the same structure as in standard text. Now, for example, if consider W dot white noise, then it is this linear expansion just with respect to one dimension of Xi k. Of course, the norm is infinity, and you have to rescale. You have to rescale somehow. How you rescale? Say multiply each term by number Rk with the property that sum of Rk squared is less than infinity. This rescaling, again, in physics is called second quantization. Expansion into Wiener chaos they call quantization. And if you want to rescale it, it's already second quantization. You give a weight. Now we could do the same thing with the equation we started considering. This is infinity. But if we select R sub n in a very simple way with positive Q, then rescaled solution will become square integral. It's not a new idea for analysis too. If something does not converge in L2, it might be a good idea to compute integral of x squared exponent e to the minus x squared dx. Weights. So weights are often used. All right, we can expand this idea of weighting on general spaces. Nothing is changing. And we, with this, we have each sequence of, there are many continuum of possibilities in weighting. So we will denote a generalized x-valued random element is the union of all weighted spaces. So it is really a very generalized stuff. The three main operators of Malliavin calculus are, as we know, divergence operator, also known as Skorokhod integral, Malliavin derivative, which is adjoint to Skorokhod integral, and Ornstein-Uhlenbeck operator, delta of D. So to say, three musketeers of Malliavin calculus, Athos, Porthos, and Aramis. There is also D'Artagnan in this game. It would be weak product. He's a funny guy, and we will investigate later on the relation of weak product to main operators of Malliavin calculus. So now let's try to define all these operators with respect to arbitrary integrator. Integrator will be U, and arbitrary integrand. Integrand will be V. F is a generalized integrand, generalized element, random element with values in the product X, direct product X is space of values, U is the space related to white noise. Then the Skorokhod operator will be defined in such a way. So we see that we have again expansion, Cameron-Martin expansion of Skorokhod integral of F, where the coefficients are given by this formula. F is a convolution with elements of U, with elements of the integrator. The simplest case when U is one Gaussian random variable. In this case, delta k of xi alpha is just a shift. You add to alpha sub k, because you integrate it with respect to xi sub k, and multiply by alpha k plus 1. Let me use this. Now, another example is Skorokhod integral with respect to white noise. It's on the bottom. It's the same structure, but simpler. Similarly, we will define Malliavin derivative. Again, V is integrand, U integrator. These are generalized random elements. You define them as Cameron-Martin expansion, and these are the coefficients of this expansion. If white noise is just one random variable, it is again very simple. You shift xi to the left by 1 with respect to xi k. So physicists call this operator with respect to xi k delta and d. D is called annihilation operator, and delta is creation operator. Now, what is happening in the case of white noise? It's a comparatively simple particular case of what we do. In contrast to Malliavin integral, Malliavin derivative, neither for standard white noise, not for generalized white noise or generalized process, is not immediately defined. You need to introduce additional requirement on this just to make this some converge in some sense. And that is also a standard for classic Malliavin calculus. Now the last one, Arnstein-Uhlenbeck process. Arnstein-Uhlenbeck process, it is an application of derivative to integral defined in this form, and again it not always it is defined, but it is important operator. Suppose U is white noise. Look at how Arnstein-Uhlenbeck of white noise works on V. It expands it in this series, and if we take as V, sorry, it should be not V here, the advantage if we take Xi alpha as V, and then we see that the Cameron-Martin basis is essentially the set of eigenfunctions of Arnstein-Uhlenbeck process. It's a known fact, but it's helpful to keep it in mind. Let's consider extreme example. Suppose U and V are white noise. What happens to Skorokhod integral? Skorokhod integral, easy to calculate. It will be sum of what it is, Hermite polynomials of each Xk. If you compute it, it will be sum of Xk squared minus sum of ones. Sum of Xk squared, that's essentially white noise squared, plus or minus infinity. But in its core, it is correctly defined. Same with Malliavin derivative. If we compute Malliavin derivative of white noise, then all U alpha will be 0 for alpha larger than 1, and only at 0 it will be a product, which of course diverges, but it is a product of ones, so it's again essentially corresponds to Wiener to Brownian motion. Now, more about Arnstein-Uhlenbeck operator. Arnstein-Uhlenbeck operator is non-symmetric. We have this inequality, non-equality, and but moreover, Arnstein-Uhlenbeck operator, to define Arnstein-Uhlenbeck operator, we have to apply Skorokhod integral to the divergence of V. But divergence is not always defined. An interesting fact, I don't know if it was known in, Marta should know, in standard calculus, of course it should be, but nevertheless, in some cases, Arnstein-Uhlenbeck operator could be correctly defined even when the Malliavin derivative is not defined. An example is Arnstein-Uhlenbeck operator of white noise with respect to white noise. It will be white noise. So there are some interesting quirks. Now, well, maybe before I go into this, again, I repeat the main points. We're trying to solve stochastic PDEs which are not solvable in classic form, but they could be solved if they are considered as a Fourier series, stochastic Fourier series for the particular equation. The series by itself does not help. It needs to be rescaled. You want to rescale it in a minimal sense, quote unquote, so that it becomes sensible, becomes convergent. So that is the main problem. Turns out that technically it is not an easy problem. Both the Skorokhod integral and the Malliavin derivative are bilinear operators. So they behave like this. But if you want to apply this to SPDEs, you need at least something like this for any one of them. You need to be able to take a norm of operator applied to a solution in some space, and there are two variables always, they are bilinear, and to prove strong continuity or by boundedness with respect to each other. In L2 it's not going to happen. So your choice is to find spaces h, y, and x. To find spaces in reality means to find scaling, because spaces you more or less choose, you look at the operator where it lives, and it blows up. So to prevent blow up, you have to find appropriate scaling, and this scaling again should be reasonably, you could take convert everything into zero, scale on infinity, and that's it. It has to be reasonable. So technically that was the crux of the matter. That's very detailed and technically complicated procedure. Now, the answer vary. You could do it in abstract setting, any spaces, take R alphas, what you have to assume about R alphas, different R prime, R2 primes, in three spaces to ensure this strong continuity. There is an answer. There are several sufficient conditions, but you could not, they would not be especially effective if you apply them to certain spaces which are more nuanced. So we did both. We did some general conditions, and we also worked on specific spaces. To two examples of these specific spaces are, one is a sequence spaces. So what is sequence space? So you choose R alpha, but this R alpha has to be a product. Everything a product. And we have infinite number of coordinates, and we weight them. We weight each coordinate specifically. So you have to have a vector of weights. One version is R alpha is equal to, say, q to the power alpha, which means that it will be q1 sub 1 by to the power of alpha sub 1, q sub 2 to the power alpha sub 2, and so on. A simple example of this, you take, say, products of all natural numbers multiplied by 2 and use them as weights. Now, another popular space is quadratic spaces, S rho L, and they have a combination of, they're also essentially power spaces, but very specific. Very specific. The powers are, in the previous example, Q you could select as you wish. In the case of quadratic spaces, this is a given system of weights, and it is convenient in many situations, not everywhere. Say if you would consider PDE even, say if you would consider du is, say, delta u plus maybe u some white noise, even of t and x, then weighted spaces is the smallest or the most convenient and exact weights. In other cases, everything depends on the particular equation. Now that is an example of a result on the strong continuity. I understand that you're getting dizzy even just looking at it, but that is what it is. You take derivative, you have to find the space, weighting. If you're talking about quadratic spaces, finding a weighting in the set of quadratic weights means find specific quadratic space. So you could formulate this in terms of quadratic space, and it looks like a usual triple. So under certain conditions, after sweating a lot, we've got the conditions which are close to optimal. Look, the constants here are universal. They depend only on one parameter in quadratic spaces, on shift, on P. Similar results can be obtained in weighted spaces. 1D example, just to show you how it works in trivial case. It's also not completely trivial space. It's 1C, but still it is not, it is anticipating situation and everything blows up. So what you do, you take F, expand F in Cameron-Martin basis with respect to this Gaussian random variable. Suppose U, F, and V are generalized random elements, and you select any three numbers, P, Q, and R, such as 1 over P plus 1 over Q is equal to 1 over R. It can be proved that if P forms a weighting sequence for U, like Pn Un squared, R forms a weighting for V, then the derivative, the Malliavin derivative of V with respect of U, that will be the nth Hermite Fourier coefficient. It will be given by this expression, and it is bounded in the norm which generated by Q. So these three numbers, they really form the basis for weighting. And this holds true practically for all weighting spaces and beyond. Now, a little bit about duality. Duality of D and delta in contractive spaces. Duality of Malliavin operator and the derivative, could be used as a definition, say, of derivative. And of course, it holds for U and V which are non-generalized, which are in L2 in any Hilbert whatever spaces. But what happens if U, V, and F are generalized random variables? It turns out that it still holds. It still holds. You have the duality, for example, in contractive spaces, and several other types of spaces. So the Malliavin calculus expands to this stuff. Now, Skorokhod integral and weak product. How they are related? If F is, I don't want to show you everything immediately. If if F is a generalized x-valued random element and eta a generalized real valued, they could not be both vector valued. One must be real valued. Then the weak product of F and eta is a generalized x-valued random random element defined by a simple formula which reminds us, which is similar to Malliavin integral. This definition, we define it like this. And this definition implies that F and eta are commuting. Say, for example, for xi alpha and xi beta, this relation is like this. However, also, if F is a generalized x-valued random variable element and eta also generalized real valued element, and then we also have a nice property that Skorokhod integral flips integrand and integrand in and integrator. But it's not true if both of them are generalized. Nothing the Skorokhod integral is not a weak product, and weak product is not defined on two generalized elements. Now, how it relates again to SPDs? Let's consider a simple, not an abstract SPDE. A elliptic operator, M differential operator in standard triple. Assume that A is coercive, and assume that A to a degree dominates Mk, or at least A minus 1 applied to Mk, each Mk is bounded. It is a weaker assumption than standard assumption which is used for space-time for coercivity. In classical case, it would be A minus 1/2 mm star should be coercive. This is weaker. Now, of course, we could find equations for deterministic for Fourier coefficients, stochastic Fourier coefficients. It would be deterministic system. It's lower triangular, and it's solvable. So you could get the following result. Assume that f is in L2 V prime, and then the propagator, and this system of coefficients is called propagator, has a solution. Such that linear combination of this U alpha belongs to some R of L2 weighted space. So that's definition. It's U hat. I am not claiming that this is classical solution. Some function which is Fourier expansion, given by Fourier expansion. Coefficients exist. What also we can also claim that there are simple weights like this. If they satisfy these conditions, simple condition, and Ck are bounds on Mk, and then everything is converging. So this field we could call, say, Cameron-Martin solution of our equation. It's not a classical solution in the eta sense. But there is no eta integral, there is no adaptivity. It is a solution. If there is a strong eta solution, it coincides with the solution. If there is not, it still exists and is unique. And by the way, it is measurable with respect to initial white noise. You don't have to introduce a new probability space, new white noise. So it is kind of an analog of, say, weak solution of the martingale problem. On some space. Here it's not on some space in omega, but in some space in space. So it has advantages and disadvantages. I probably could stop it here.
Comment or question? I was a little confused. Oh, sorry. No, go on. I'm not.
Okay.
You're not present.
I would just. So you said that in the case when the ito is defined, it coincides.
Not if there is no eta. So if there is an equation when you have a path, a solution for almost every omega, there is a random element which satisfies equation. We don't expand it in Wiener chaos. We don't compute Wiener chaos equation. Just satisfy it. And this belongs to L2. then Wiener-Calf expansion solution will coincide with this one. So it's not like in eta.
In your example, if you smooth the Brownian motion, like if you try to do Wang-Zakai, for instance,
For Zakai, yes, sure.
it will converge to your
Yes. And for this equation, say is A and sigma satisfies this condition, there is a classic solution. And Cameron-Martin solution will coincide with classic solution. But if sigma square, if this condition does not hold, this equation still has solution, Cameron-Martin solution. It is unique, and it is measurable with respect to this Brownian motion. But that's what you got. As they say in America, you got what you got.
No, but it's the limit of Wang-Zakai approximation.
Yeah.
Any more comments? I was a little confused about what you said about the Wick product and the divergence being the same. You said they're the same, but one's slide back.
They coincide when they coincide if at least one of the processes is real value. But
And both generally,
Yeah.
they could both be general.
yes, but with product as it is constructed is not really easy to generalize to random. You cannot construct eta calculus around. Look, here is a product. It is a point process. It is a point product. So if at least one of them is generalized, that's it.
Otherwise, you would have to have a tensor product.
Right. So we've tried to come up with an analog of Malliavin calculus, starting from from Wick product, but it works only in the limited, comparatively limited situations. But still general enough. Just don't mess with generalized random element.
The weights that you introduced, are they sort of something that you have to guess, or are they given by the other data?
Mostly you have to guess, but there is a number which are very convenient in many ways, and that's Kondrativ spaces and product spaces. And these are the weights. So when physicists say stochastic quantization and stochastic second quantization, especially second quantization, they explicitly have in mind that the weight should be a product of all components. And then everything works with second quantization and so on. So it's there is something very general in this which we don't know yet. But by some reason, they pop up naturally in many areas.
Thank you very much indeed.